speaker. In some sense, she will give a couple of talk in this workshop. She's Alena Zhukova from St. Petersburg, from Russia, and she will deliver her talk on moduli spaces of planar linkages. So,
thank you.
Please.
Thank you, Professor Tivari. And I thank you for the organizing this school. This is, for me, it's really exceptional experience. These days were really nice. Thank you. Yes. Okay, I will tell you about moduli spaces. I will write it here. Of planar linkages. I understand that this is the end of the day, end of the school, so everyone is tired, so I will try to make it as simple and entertaining as possible. Yes, so modular spaces or equivalently configuration spaces, I tell you because sometimes I use one term instead of the other. This term has already appeared here on the school in the lecture of Professor Roshika. Well, and I hope that you understood the main idea of this construction is constructing new topological spaces or manifolds from different mathematical objects. And here I will show you how topology, in this sense, is applied to studying to study of a very natural, simple, and used in everyday life mathematical objects linkage. Yes, so this is, in fact, this topic is very vast. It started from engineering, of course, engineering to robotics. Linkages are used in applied science, as applied mathematical model in chemistry, in molecular biology, of course, in computer science and algorithms, and so on and so on. And the mathematical instruments that I used to work with them and the results are also very, very vast from different spheres of mathematics. So I will, but I will try to tell you about two aspects. So first aspect will be about the plane. This will be the first part of my talks. So it's geometrical or engineering part. And yes, the second part of my talk will be topological, about moduli spaces. Yes, so like this. Okay, let's start with the definition. Well, the definition is very intuitive. A linkage, what is a linkage? It's an abstract linkage is a graph. You can imagine a graph, some simple graph, something like this, vertices, edges, with prescribed lengths of the edges. So if E is an edge, then we can have its length. Oh, these letters look very much like this, length. Yes, and of course it is greater than 0. Yes, so as a usual length of a real object. Yes, and this linkage, this is an abstract linkage. We can write here something like, and so on. And for this abstract linkage, we consider its configurations. In my talk, I will consider configurations on a plane, on an Euclidean plane, or you can say that it's an Euclidean plane or a plane of complex numbers. So it is an embedding of this graph. Well, in fact, we can say that we map the vertices of this graph in such a way that if we have an edge, then the distance between the images of the vertices will be exactly the corresponding length. So it's like a real object that lies on a plane with these restrictions. Yes, and we are interested in the way how this object can be placed on a plane and how it can move. So if it's a linkage, we can imagine that these are bars that are joined by hinges, right? The English word, the hinges, and they can revolve around these hinges. And well, in general case, of course, well, it moves on a plane, and we will let it intersect itself. So it can move, change its configuration. I don't know, something like this, yes. This will be the configuration of the same linkage with the same length. Yes. So again, we have this F, and for an edge between two vertices, if we have an edge between two vertices, then the distance between their images will be exactly the length of this edge. In fact, we do not necessarily need to place our linkage in R2. In fact, we can consider configurations of a linkage in any metric space that we like, in Euclidean, in non-Euclidean, and well, on a sphere, well, anywhere. But the plane is the simplest and the most natural example. So today we will consider linkages on a plane. Okay, so so we have an abstract graph. We have vertices and edges, and this F is a function that places our vertices on a plane. So here is an abstract linkage, and here is a picture on a plane. So here we have a vertex, for example, V, and here we have its image on the plane with coordinates and so on. Yes. Yes, yes, yes. Yes, yes, yes. Right. Okay, so usually when we consider the movement of a linkage, we can fix some vertices. So if we do not want it to move just by rigid translations on the plane, we can fix, usually we fix one vertex or we fix one edge, the position of one edge. So yes, this is the mathematical model of real construction. Yes, yeah.
So what is this mod? The mod of FV, FW. This is the
Usual distance on the plane.
Euclidean distance?
Yes, just Euclidean distance between the 2 points. Well, just it's a formal definition.
But when you were in that graph, there was another distance, right? The graph metric.
No, distance between, so we have an edge of length. We are interested only in the distances between our vertices. Only if there's an edge between two vertices, we are interested. So the distance between two vertices is exactly the length. Well, yes, just like a rigid bar that is situated on the plane. Yeah, no, just an.
There is no metric on the graph?
No.
But then what is the phi? So phi is the length, just the length of the edge.
Just the length of the. No. Of course we can.
So like. So the domain of this map is a metric space. Right?
No. Only the vertices. The vertices. We insert the vertices. No, forget about metric space. We just take a vertex and place it somewhere on the plane. Take another vertex and place it on the plane, and so on, so that it is the linkage construction. So we have. No, we do not. We're not interested in metric on the graph. It's another. No, not necessarily. We let it. You see here, it can intersect itself. We let it intersect itself. No, of course not. For example, if I have such an abstract linkage, a graph with such length, of course, it's impossible to embed it into a plane. Yes, so this is an abstract linkage that has no configurations, empty set of the configurations. Yes, if we have something nicer, like a triangle, like this, and for example, if we do not want it to move, we can prescribe that this point has coordinates 0, 0. This point has coordinates 10, 0. Then what are the possibilities? In fact, we have only two configurations, right? We can place this vertex here or here. Two configurations, two points. Yes, but this is not very interesting because in the engineering sense, we're interested in motions of our linkage and movements. So, so let us consider something more interesting. Well, the next example is a pendulum. So suppose we have such very, very simple graph, two vertices and an edge, and we embed it on our plane. We place it on our plane like this. We fix one vertex and another is free. And here we have a length. Well, it doesn't matter. So this vertex can travel on a circle, right? So the possible configurations look, I'm not very good in drawing circles. Well, suppose that they all have the same length. So all the possible configurations, they look like this. And this vertex, if we, for example, you can use it as a compass. If we are interested in all possible positions of exactly this vertex, we will have a circle. So this is a very simple linkage that can draw a circle. Good. What else can a linkage draw on the plane? Suppose we have a quadrangle, something like this, a very flat quadrangle. Yes, and we fix these two vertices. How does this look on a plane? So these two vertices we fix, and these two vertices can travel on our plane. So what is the geometric place of all possible positions of this vertex? How does it look like? Where can this vertex travel on the plane? In fact, it would be a circle if not these two links. So somewhere on this circle, so here we have the same pendulum, somewhere on the circle it stops because these two edges are aligned and they will not let this vertex go further, right? And on the opposite side as well. Here again, we have these two edges aligned. So it's a segment, right? So the set of all possible positions of this vertex is a segment. Yes. It may seem that these two configurations on the end of the segment, they are in some sense special, but in fact, if we will be interested not in this vertex, but in this vertex, of course we have the same kind of things. We have a segment here, and from this point of view, from this segment, these two configurations, they do not have anything special. Yes, so this vertex can draw a segment on a plane, and this vertex can draw a segment on a plane. Any questions? No? Okay. But with this quadrangle, we can do something more interesting. We can place our pen somewhere here in the middle of this edge. So suppose these two vertices are still fixed. So what figure will draw this point? What figure this point will draw during all possible movements of this quadrangle? What it will look like? Try to imagine. Like what?
You will move these 3 points?
No. We are considering all possible movements of this construction, and we watch what figure will be drawn. So what figure will this point draw? Like what? Try to imagine. Use your geometric imagination. In fact, we can move it, so this edge can move like this or like this. Yes, so we have, in fact, a lot of possible like this configurations. But this point, if you try to imagine it, it will give you something like number 8. Well, you can try to draw it in a computer program. It's not so complicated. So this is a more interesting curve. So we can use linkages to draw interesting curves on a plane. We already have a circle, we have a segment, and now we have something like this. Well, of course, it is not hard to derive a formula for this curve using the length of our edges, but we do not want to do complicated things right now. We just believe that we can do it, yes? So, yes, a curve like this. What else, what other curves, or maybe not only curves, can a linkage draw? An interesting question in 19th century, where, of course, interest in such things was raised in 19th century during Industrial Revolution in Europe, where everybody starts inventing some engines and mechanisms and so on. So interest in these construction raised, and a problem to construct a linkage that can draw a piece of a straight line was raised. Yes, and it was solved by 2 people in the same time, by Lipkin and Posselier, by constructing a special kind of a linkage. So we will start with a construction like this, a symmetrical. I hope that it will be symmetrical. Okay, so all these bars have the same length. Well, suppose here we have length A, and here we have length B, and this is all symmetrical. Therefore, on the plane we have a symmetrical configurations. So here we fix it, and this linkage is called inversor. Am I telling this right in English? Inversor, right? Yes, inversor. Why? Because if we consider this as a 0, if we consider our points as complex numbers, we can do this, of course. If this fixed point is 0, this point is z, a complex number, then this point will be square root of a square minus b square divided by z. So this number is not so important, but this thing is important, that it inverts our z. And therefore, so this point, the coordinate, well, the complex number that this point represents is in some sense the inverse of this number. This is very nice. Why? Because, well, this means that this point is an image of this point with respect to inversion by this circle. So I have this circle with this radius. So we can say that this linkage, it calculates the inverse of a complex number. So if we move, we take this point and move it somewhere on the plane, then this point will be exactly, well, if we want to well, we'll calculate exactly this function. Hmm? Why?
Because if the point C turns like a watch, the other turns like a watch turning in the other direction. So the usual
No, if we turn it, it will turn. Yes, so if we turn it like this, no. Ah, yes, yes. I'm sorry. Yeah, right. Yes, right. I'm sorry. Maybe I made a mistake. Yes, right, exact. Yes, because I didn't write it here, so I made a mistake. I'm sorry, and it's hard to think when you. Yes, well, this is not. Well, we can do something with this. Okay. So this is a linkage that calculates some kind of function. So linkages can be used to draw a line or to calculate a function on complex numbers or on a set of on several real numbers. So, and this inversor can be used to draw a straight line. How? If we place a point here, fix. So we attach a pendulum here. So this is exactly in the middle between 0 and z. Then this z will travel only on one circle with the center in 0, and therefore this point, as a function of these points, will travel on a piece, on an interval of a straight line. So this is the Lipkin-Poiseuille inversor, or a straightener, that can turn a segment. In fact, it's a segment. It cannot travel all the circle. A segment into an interval of a straight line. Piece of circle. Yes. So this inversor can calculate an inverse of a complex number. And if we have any other linkages that can calculate other functions, then we can calculate more complex functions. So we can calculate polynomials, or rational functions, and so on. So, for example, how with use of a linkage calculate a scalar multiplication? For this, so this is here. We can calculate an inverse. Well, after some adjustments. The next linkage is scalar multiplicator. Oh, it's also called pantograph. Yes, and it's used in drawing, in engineering, and so on. So it's constructed like this. Here we have two long bars. Here we attach a bar. We attach a bar to a point on another bar. But so this is not. Here we do not have any linkage. We can make it rigid like this. We can add one bar like this. So something like this. You see here we have similar triangles. Here we have, again, 0. Suppose here we have x, and here we have lambda x. So if here we have z on the same plane, then here what do we have? we have, so this triangle is similar to this triangle. So here we will have lambda z, right? So this is a scalar multiplicator, a linkage that calculates, that multiplies, again, a complex number by some, well, in this case, positive number lambda, like this. It's so that it's, in fact, it's for rigidity, so that it doesn't bend in this point. We're not interested in bending in this point. If we want it to stay straight, and for this case, we just add one extra bar. Again? Well, I put an extra bar to make this hinge rigid. So I'm not interested in bending here. I'm interested only in existence of this triangle. So you can imagine that it's how it moves. Well, you can, yes. So this is a scalar multiplier with the same, in the same manner. We can use linkages to add one complex number to another. We can use more linkages to multiply one complex number by another, even though this linkage is very complicated and I will not be able to draw it on the board. Yes, so in fact, with these linkages, yes, we can calculate any algebraic function, but of course there are restrictions, in fact, because you understand that even though, for example, here we can multiply number by lambda, we cannot multiply with this linkage all numbers on our plane because, yes, it has some range. So this vertex can travel only on the circle, inside the circle with center zero. So in fact, this linkages can calculate functions, but only in some domain, right? Domain. Yes. So and then in all this field, in what can a linkage draw? In attaching one linkages to others, in fact, there can appear some problems. For example, if here we have a parallelogram, right? And the linkage that is a parallelogram, he can have not only configurations like this, but, for example, configurations like this, anti-parallelogram. And of course, this will a little break our construction, but these things can be fixed. And the main result in this field is that the theorem that was stated by CIMPA, but in a very vague form. And this theorem is called Thurston's signature theorem. Maybe I will erase all these things and write. So the main result on the plane, the main geometric result in this field is, you can call it signature theorem. That for any real algebraic curve, on the plane, there exists a planar linkage linkage L, well, it doesn't matter how, which draws, in fact, in some domain, this algebraic curve. That means the locus of a certain vertex L, the locus coincides with this curve. Well, yes. Why is it called signature theorem? Because you can for your signature you can express your signature with some precision as a real algebraic curve, and this theorem says that there exists a linkage that can draw exactly your signature on the plane. So this all can be performed mechanically. So this is the story that that is there on a plane if we do not exit the plane, and if we talk about these things in geometrical sense.
So what do you mean by algebraic? What do you mean by algebraic?
Well, a curve that is described by algebraic equations. Yes. So this is the main result on a plane, and now I will show you how we get the second element of my talk, the moduli space. If there's no questions about this.
Can you speak more? I mean, what is the locus here? What do you mean by
Locus,
locus?
it's the set of all, locus is a place, so it's a geometrical place of all possible positions of this vertex. So for example, for a pendulum, it was a circle. For a quadrangle, it depends on the point. If we take these vertices, then it will be a segment. If we take this vertex, it will be this curve that resembles number 8. Yes, and in general case, this line that is drawn by a linkage can be as complicated as you wish. Yes, and yes. This is the universality theorem for linkages in most simple in most simple.
This is like inverse of what you said in the beginning. You moved in the beginning from curve to the graph.
From what curve?
Graph. Sorry, in the beginning, the first graph.
Yes, from what? Graph. Yes, this is yes. And if we are interested in a vertex of this graph, so this whole graph can bend and it can travel on the plane. Yes, but we are interested in the behavior of one vertex. Yes, so this like this.
So this is like inverse of this. You move from plane to.
Yes, in some sense, yes. But in fact, the proof is not constructive, so it's not so. Well, in fact, it's not. It's of course, it's if you have if you have, but no, if you have just a real equation, yeah, you can construct a linkage that draws this real curve. Yes. But of course, it will be very complicated. If even the multiplier is so complicated that I wouldn't draw it on a plane. Yes. So how do we?
Is there any algorithm that will help you figure out the linkage?
Well, if you have a formula, so you see that we have a linkage that performs multiplication. We have a linkage that performs addition, and so on. So if you attach one vertex of one linkage to another and add some more things to avoid the degenerate construction, yes, so then you will have a linkage that calculates an algebraic function. Yes. Well, in a naive way, you can yes.
Given such a real algebraic curve,
Mm-hmm.
is there a upper bound of on the complexity or the number of hinges you need to use at least to
This is a nice question, but in fact,
in this proof is there some
well, in fact, I do not remember. Yes, because yes, but yeah, this is a good question about upper bound.
so this was constructed by Thurston,
Yes, this is Thurston signature theorem. It was formulated in this way by Thurston. Yes, and the proof, the whole proof. I forgot the names. Do I? Yes, right. Thank you. So yes, the whole proof of these things can be found in work of Kapovich and Milson. In fact, they prove their a set of universality theorems about linkages, not only about the things that happen on a plane, but in moduli space as well. And they use, in fact, quite complicated algebraic geometry. So if you will be interested, be ready. Well, no, in this sense, yes, because they use these linkages that can calculate. But this is not constructive for other universality theories. Yes. So now I have time to tell you how topology appears here. Well, in fact, this part is over. So this is the main theorem. So the algebraic things on the plane. If no questions about it, then I will tell you how topology appears here. No? Okay. So in fact, so far, I've shown you only the linkages with 1 degree of freedom that draw a line on the plane. But in fact, we can consider something like this, a robot arm. Yes, so here, well, a typical object in robotics. So this point can move on a plane in 2 dimensions. It has, well, you can imagine this, right? So it has 2 degrees of freedom. And if we are interested, well, this is completely another task about linkage. So if we are interested in in programming, for example, the movements of a robot arm, we are interested in how this space of all configurations looks like. So how can we think about this thing? So I remind you that we have graph, we have a configuration on a plane, and how can we encode this configuration? We can, for example, take all the vertices, well, in fact, not fixed ones, and write down all the coordinates of the vertices. First, second, and so on. Oops, this is y. I don't know how many n, right? So these are all coordinates of all vertices of a configuration. And this is a point. This is a coordinate of a point in this space. And so if we take all possible configurations and encode them like this, all possible configurations of our linkages, we will get a subset, well, or subspace, of course it inherits topology, a subspace of this space. So something that lies inside this space. Yes. And space of all configurations. We denote it like this, M, modular space of a linkage. Yes, it is a subspace of this Euclidean space. And, well, in fact, how can it be created in this, where is it in this space? In fact, it's a algebraic variety that is defined by restrictions of the length of these bars. So it's just, well, in fact, of these equations. So it's well, it's a point in R square to the power n, such that for every edge E, for every edge, let's say from vertex V to double V, well, X, I forgot. Is equal to length of this H square. So it's just a set of equations of power 2. So it is some real algebraic variety in this space. Yes, how does it look like in this sense? Some practical example. For a robot arm, let's see. How can we see this? Because, yes, this dimension is quite large in general case. So here, how can we see our configuration space? On the plane, we have this point that travels, and what are the possible positions of this point? Right, right. Well, let's denote it L1, L2. Let's say that L1 is greater than L2. Yes. All the possible positions is in annulus. Here we have the radius L1 minus L2. Here we have radius L1 plus L2. Yes, this is one approach. Another approach is how can we parameterize our configurations. For example, we can say that for every possible angle phi1 here, and for all possible angles phi2 here, we have a configuration. So these two angles define in configuration in a unique way. So this angle is a point on a circle, right? And this angle is a point on a circle. They are two independent, so the space of all configurations of a robot arm is a torus. S1 times S1. This is a configuration of our linkage. So here we have a torus. This is a configuration space. And here we have, for every configuration here, we have one position of this vertex here on the plane. And so for every configuration, we can, so we have a map from configuration space to onto a, no, in plane, not onto. This is, yeah, this is wrong. How does this map look like? So this from a configuration to its endpoint, from a configuration to its endpoint. So if our endpoint is somewhere inside the annulus, what is the pre-image of this map? So what configurations correspond to an endpoint like this? Well, how many? How many configurations can we have with our robot map if our endpoint is situated here. 2, right, 2 in 1, like this, right, and like this. So for every point in the interior of this annulus, we have 2 possible configurations. And if we have a point on in the boundary, then 1, right? Because here we have an aligned configuration like this, and here we have another aligned configuration like this. And if we try to mirror them, then nothing changes. So we have 2 copies of an annulus that are glued along their boundaries. Yes. So this is how this map works. And what happens, for example, if our lengths of bars are equal, L1 is equal to L2? How does this work? Then the set of all possible positions of this endpoint, how does it look like? Yes, but I'm asking you about the workspace, the space of all possible positions of this endpoint. Well, if they are equal. Nothing, in fact, it's just a punctured disk, right? So in fact, no, just a disk with a special point here. So it's just a disk, right? And if we have, here we have a special point, and if we take any point on this, so yes, so this point can travel from 0 to L1 plus L2, right? So anywhere on the disk. If we take a point from the inside of the disk, except the center, then how many configurations correspond to this endpoint? Again, right. So if our endpoint is here, then we have 2 configurations like this and like this. Again, so the pre-image of interior, except this point, is for every point, the pre-image is 2 points. From the boundary, again, 1. And from this 1 point, yes, but topologically, yes, right. So here we have a circle. The pre-image of this point is a circle, because we have this degenerate aligned configuration. If one bar lies on top of the other, then it can just revolve the whole circle around the beginning, around the 0. So the pre-image of this point is a circle. And we have, again, this outer circle, and which is the pre-image of boundary of our disk, and between them, 2 copies of a punctured disk. Right. Another example. So this is the robot arm. It has its configuration space is a torus. Let's return to our next example, a quadrangle.
Modular space of L1 is isomorphic to modular space of L2. L1 and L2 are same.
In case, you mean for these 2 robot arms?
Say any L1, L2 are there.
Yeah, so for any robot arm, it will be torus. So all robot arms topologically are the same.
In general, some L1, L2.
Yes, if you have a robot arm, then it will always be a torus. If you have a robot arm with more bars, yes, if you need such a robot arm, then you fix the beginning. Yeah, so you can parameterize it with angles, with these angles, and so on. So its configuration space will be S will be a circle to the power n. Yes, so some high-dimensional torus, right? Yes, so all robot arms look exactly the same. From their topology look exactly the same, but we will need them for other examples. Let's see. Let's return to our quadrangle. Well, suppose we have, again, a quadrangle. These two vertices are fixed. And suppose we have, so we are interested in, now not in the trace, we're interested not only in the trace on plane, but in our configuration space. So how can our configuration space look like? Again, this point can travel on a segment with two endpoints. Here we have an aligned configuration. Here we have another aligned configuration. So who can tell me what is the configuration space of such a quadrangle? If this point can travel on a segment from one configuration like this to another. So we have, again, we have all possible configurations of a quadrangle, and for every possible configuration of quadrangle, we have a position of this point. So if this point is, this vertex is here or somewhere here, how many configurations correspond to this position?
But from 2 points, all are exactly 1.
No, look, if we have a point and we're interested in configuration of a quadrangle with this point, then we can have it like this, for example. Something like this, right? And another configuration of this quadrangle can be something like this. Right? So every point in the interior of this segment corresponds to two configurations, and the points on the end of this segment correspond to one configuration. So the configuration space of such a quadrangle is just a circle. Yes, and but in fact, we can have another type of quadrangle if this bar is short enough to make a full circle. So for example, we have something long, then again something long, and this is very short. Then this vertex can make a full circle. Yes, there are no restraints. So, and how does this configuration space look like? What is the configuration space of such a well, in fact, for every point, how many configurations are there for every point on this circle? Yes, so this is just two circles, S1 and S1. Yes, just disjoint union of two. In fact, I'm not very sure what to do now, because if I have only 5 minutes left, and if I start now with with polygons, then I will maybe I will tell the other things on polygons and spiders and robot arms in the next tomorrow. Is it okay if I finish now? Yes. Okay. So these are the examples. So we know what moduli spaces are. So how they are created from geometry and from geometry of these linkages. And tomorrow I will tell you the results about the configurations about the topology of these configuration spaces of linkages. Yes. Maybe you have any questions? So yes, we have a story on the plane. From this, we created a topological object for every linkage. Yes. Okay. I will try to remember. Okay. Very easily. So suppose we have let's have two robot arms, right? So, with one and the same end. Suppose I have, but I will make them. Yes, the pentagon, very narrow pentagon, like this. So let's see how this point behaves, the common end of two robot arms. So this robot arm has a domain on the plane. It's an annulus. And this robot arm has a domain on the plane. It is annulus. And if we choose the lengths carefully enough, then the intersection of these two annuli, right? It will be this piece of a plane. Yes, so it's just topologically it's just a disk. Yes, and what do we know about this disk? So for interior point, how many configurations correspond to this interior point? There are two possibilities for this robot arm and two possibilities for this robot arm. So in fact, 4. Yes, so this point corresponds to 4 configurations. So we have 4 copies. So if we consider it as a pattern for sewing, then we have 4 details like this, right? What is the preimage of this point on the boundary of one annulus? Yes, now it's 2, so somewhere here. This one and, for example, this one. And for the intersection of the boundaries, yes, so all of these points should be glued together. Yes, and you can see that if we glue these 4 details together, what we have is a two-sphere, right? So this is an example of a two-sphere. Yes, like this. So these are the examples, and tomorrow I will tell you the main results about the topology of the configuration spaces. Thank you.